Hey, feeling good, like I should. When in dark, walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at the homework for lesson 2.3.2. We are going to look at the M&Ms for creating intervals on your number lines and the proper scaling, which refers to, the counting sequences. So, if you consider this being the x-axis for a graph where the x-axis represents how old something is, if you need to get up to 80, you can do it and you can count by 5s, you can count by 10s, you could count by 2s, you could count by 4s. How you choose to space that out is entirely up to you, but each one of these has to be the same distance and it has to follow a counting sequence. So if you're going to take 1, 2, 3, 4 steps to get to 80, you have to take 80 divided by 4, which means every one of these is going to be counting by 20. So this should be 20, this should be 40, this should be 60, and then that is 80. So very, very important when you're creating number lines, it's properly scaled. The tick marks are all evenly spaced, and the counting sequence follows a clear counting interval, whether you're counting by 5s, counting by 10s, counting by 2s, counting by 1s, it doesn't make any difference. Just make sure that the entire number line is consistent. Troy is a fan of baseball, and his favorite player is Mo Jower of the Minnesota Triplets. Troy made a display or a table displaying how many home runs Jower hit during his first 5 seasons. So season would most likely in this case be on the x-axis, and the number of home runs would be on the y-axis. And so you treat this as ordered pairs. So season 1, he hit 6 home runs. So that would be like x is 1 and y is 6. So we plot 1, 6, and that would be the first season. Season 2, he hit 9 home runs. So you go to season 2, and then the number 9 goes right here. Season 3, he hit 13. So season 3, 12, 13 goes here. And then season 4, he had 7 home runs. And season 5, he had 9 home runs. So the idea of taking each one of these quantities in the table and have one of those quantities be referenced on the x-axis, the other quantity being referenced on the y-axis, they form ordered pairs that can be plotted onto the graph. Sarah turned in 2 graphs below for homework. The teacher marked them wrong. What did she do? Now, this is a stoplight problem, which means that there's a very common mistake that is made here. So what's the mistake that's made here? Well, here, look at the counting sequence along the y-axis. Are you counting by 1s? Are you counting by 2s? Are you counting by 4s? There's a mistake there. You should be having either counting by 1s, 1, 2, 3, 4, or counting by 2s, 2, 4, 6, 8, but you can't have a change in the counting intervals. So that is not scaled properly. Here, they don't have, their origin is supposed to be 0, 0. This origin appears to be at -1, -1. So that's a mistake. So how would we fix those? Make sure that your y-axis is properly scaled, and you can kind of see a growth pattern here where this is called exponential growth or nonlinear growth. And then here, now that we've got our origin in the right location, this is a more accurate graph. If a set of XY axis has 20 grid units in each direction and the greatest value of data to be placed is 132, what would be an appropriate and convenient scale to use for the axis? This is a big problem. I mean, I find myself doing this all the time. If I need to fit in the number 132 and I don't have enough squares, I think, to count by 10s or count by 20s, you got to make it work. So in this case, just take 132. If you have 20 grid units that you can use, then you could count by 7, but I'll be honest with you, who wants to count by 7s? I would count by 10s instead. That seems like it would be a lot easier. So, maybe 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150. I'd probably just stop at 150 and label the 50th, 100th, and the 150th. To me, in the amount of space that we have available here, seems like the best way to go. If you counted by, say, 20s, then you would only have to go to here. If you counted by 5s, I wouldn't have enough room to fit everything on there, since 5 times 20 is 100. You'd never make it up to 132. So it's, you know, trial and error. The more times you do the graphs, the easier it becomes. But what you basically want to do is be able to fit all of your data and have it be as spread out as you can possibly have it, while still having all of your data fit onto the graph. Simplify each expression. All right, so in some cases, looks like most of them have fractions times fractions, but here you've got a fraction times a decimal number. So you've got to make the choice. Do you want to change this to a decimal, or do you want to change that to a fraction? Since 2/3 is 0.6 repeated, I don't know how to multiply. No, that's not repeated. I don't know how to multiply a repeating decimal times anything, because it just doesn't really work. So that's why it's so important for us to learn how to deal with fractions, because repeating decimals can be very difficult to work with when you're trying to do calculations. So 2/3 times 8/10, that's a little easier. You get 16/30. And of course, 2 goes into both of them, so that can be simplified. Here, 4 times 3 is 12. And 3 times 7 is 21, but you may recognize that you can cross cancel the 3's and leave you with 4/7. Same idea here. You know it's a negative times a positive, so you're going to get a negative answer, but you may choose to change that to a 2 and this to a 3. So -5 times 2 is -10, and 3 times 7 is 21. Had you not done that, you'd have gotten -20/42, which would have to be simplified, dividing the top and the bottom by 2. And then for problem D, I recognize that a negative times a negative is going to give me a positive answer, so I'm just going to ignore the fact that there are negative signs there. And I'm going to change this to, instead of 1 1/3, change it to 4/3, so that when you multiply straight across, you get 16 on the top and 15 on the bottom, which then can be changed to the mixed number 1 1/15. For each of the experimental results described, write the indicated probability. So you flip a coin 80 times, and there are tails 47 times, which means the rest of them had to be heads. And 80 minus 47 is 33. So the experimental probability of flipping a head, in this case, was 33 out of 80. Not the same as the theoretical probability, which would be 40 out of 80, or 1/2. But, you know, experimental probability doesn't always match the theoretical. That happens. A bag containing purple and orange marbles Sam has, and he wants to randomly take out one marble and then return it to the bag. So he does it 18 times. And 12 of those 18 times, an orange is pulled out. So the probability of pulling out an orange would be 12 out of 18. Which means 6 out of 18 would be purple. And why are they asking us about green? There were no green. So 0 out of 18 is the same as 0. Sarah pulls a card from a standard deck and then replaces it. Remember, there are 52 cards in the deck. She does this 30 times, and 40% of the time, it's a hearts. So what's the probability she will not get hearts? Okay, well, and we actually don't even need that right there. So we've got all the information we need right here. So if 40% of the time she got a heart, then the rest of the time, which would be 60%, would be not a heart. What work did I show down here? Do we really even need that? I guess maybe, maybe not. I don't know. So 60%, I think that's all we need. This probably isn't even necessary. Use your reasoning about numbers to answer the following questions. If multiplying by 1/4 makes a positive number smaller, then what does dividing by 1/4 do to that number? Well, if you divide by 1/4, it would make it bigger, right? It would make the value greater. Let's actually show this. If you take 2, a positive number, and divide it by 1/4, what you are asking is how many 1/4 can you fit into the number 2? So if I go and I take, there's the number 2, and how many 1/4 can I fit into that? Looks like I can fit 8 1/4 pieces into the 2. So that's what's happening whenever we're dividing numbers by fractions. We're asking how many of these can fit into there. Let's do a more simple problem. How many 2's can you fit into 6? Well, you can fit 3 of them, right? Because 3 times 2 is 6. So same question, just a little bit easier to picture because we've worked with these types of problems for a number of years now. But the same question applies when you're dividing by fractions. How many 1/4 can you fit into the number 2? You can fit 8 of them. What's the next question? If multiplying by 1 does not change the value of a number, then what effect does multiplying by 2/2 have? Well, it's the same since that's a giant 1. Whenever you multiply any fraction times a giant 1, you're not changing its value. So if I took 3/5 and I multiplied it times 1, you would still get 3/5. So when I multiply times, that's supposed to be a 2 there, by the way. That's terrible. Sorry. OCD. Must get that neat. There you go. So while the fraction, the new fraction is 6/10, it's still equal to 3/5. And that's the whole basis for us using the giant 1 to create equivalent fractions. Equivalent meaning equal to. Problem number C. If you find 80% of a number, do you expect the answer to be greater or less than that number? Well, 80% is less than 1, right? Since 100%. So what is 100% of 10? It would be 100%, right? It would be 10. So if we took 80% of 10, it would be 8. And 120% of 10 would be more than 10 because 120% is more than 1 or more than 100%. So that would end up being 12. So when you multiply times a percent that is less than 1, your number is going to go down. And if you're multiplying times a percent that's greater than 1, the number will go up. All right, that does it for today's homework. And I believe we are going to get ready pretty soon for our final chapter test of Chapter 2. So let's get go in that direction. Take care. Bye. Bye.
Hey, feeling good, like I should. When in dark,